Alright, so welcome back. We are going to get started with the data visualization lab. In this lab, there are three parts. There's a visualization about flowers, a visualization about chicken weights, and a visualization about air quality. If you are following along in the written guidelines, you only have to do two of the three, though I'm going to record them all as one big unit here. So the visualization about flowers, everyone has to do. Chicken weights will give you an opportunity to do some categorical visualizations, and air quality will give you an opportunity to work with time series. So which ones of those two that you choose may have to do with what you anticipate your final project to be. I do encourage you to do all three because I do think that all three are quite useful and interesting. Alright, so for this lab we are going to install a new package. We're going to install the GG Themes package. So install packages, and we're going to pass GG Themes. As you can guess, this goes along with things like ggplot, which we've used previously. You do have to be connected to the internet to make that work. Alright, once you install it, we are going to call it. So we'll call the library GG Themes. We're also going to use the tidyverse, as we always do. We're going to use Dippler and Lubridate. So library DPLYR and library Lubridate. Alright, so let's go ahead and run all of these, and those will load. So by the end of this lab, you're going to be familiar with the ggplot library and some basic principles for communicating with visualizations. Now, you are not going to be an expert in all types of visualizations because we can't do that in this short of a lab. But you'll have the tools in order to communicate visually with data, which is really where you need to be at by the end of this class. Alright, so the first thing we're going to work with is flowers. And this is a super famous data set. It's the iris data set. And it has to do with flower petals and flower sepals. So petals are the colorful bits of a flower. So when you look at a flower and you're like, oh, it's so pretty, you're probably reflecting on the petals, right? That's the thing that has like the bright reds and the purples and the blues. The sepals are the part that holds up the petals. So if you've ever turned a flower over and looked at the bottom, that little green bit that's like much harder than the petal is holding it up. So it's like attaching it to the stem. All right. This is like a super detailed data set. And you can go ahead and look at it. It's called the iris data set. But it's way easier to understand what's going on with everything in this data set if we visualize it, because it's really hard to make generalizations based on a table. So we are going to first do an exploratory analysis. We want to see how variables are related to each other, see if there's any trends. So through the course of this tutorial, we're going to plot sepal length and width against each other. We're going to differentiate by species. We are going to find the line of best fit, and we're going to format your plot. Formatting is a oft overlooked but crucially important part of doing data visualization. All right. So the thing that you will submit are your final plots. For this, if you got your plots to work, I know that your code works. So all you need to submit are your plots. All right, so let's get started and look at this data set. All right, so the data set is called iris. I'm going to type $iris and run that. And it's going to give us a little bit more information. So I've always known this as Fisher's iris data set. It's 50 flowers of 3 species, and it's just really cool. Go ahead and look up the history. That's not relevant right now. All right, so let's load it as data. So we'll call that in. And then we'll ask for a summary of the iris data set, and we will ask to glimpse it. All right, so let's look here at our summary. What we have 4 variables. We have, well, 4 quantitative variables. We have sepal length and sepal width, petal length and petal width, and then the species. And there's 50 of each species. All right. You have the averages here, what the maximum values are. We see that it's all like pretty small, easy to deal with numbers. All right. We see they're all in decimal format except for the species, which is a factor. That's great. And as you can tell here, it is really hard to get a sense of this data just by looking at these numbers. So we're going to visualize it. All right, let's look at how it's formatted. So we'll look at the head of the data set. Excellent. Looks like we got our 5 columns here, exactly as we would have expected. Not seeing anything null just yet. Let's check to make sure there are no null variables. So I'm going to go sum is NA and then iris. This will tell me throughout the entire data set how many NA values there are. And it looks like there are none. Excellent. So we know that this data set is very clean. All right, so first thing we're going to do is get started with an exploratory analysis, like just purely exploratory. We're going to make a scatter plot, and we're going to use the point geometry, and we're just going to look at sepal length and sepal width. Okay, so I'm going to call ggplot, and I'm going to pass it the iris data set, and my aesthetic is going to be x equals sepal dot length, and y equals sepal dot width. And then I'm going to say, give me a point. All right, I'll run that. And excellent, we have our points over here. Now, a lot of these points are on top of each other, like directly on top of each other, which is not particularly helpful. So we are going to go ahead and jitter them, which means move them over ever so slightly. The mathematical representation of them isn't going to change, but the visualization of them is going to change ever so slightly. Rarely when you're making a visualization is precision the most important part of that visualization. Usually you're looking for trends and like overall patterns. So jittering this data just a little bit is going to help make our visualization easier to understand while still allowing us to see the rest of the data. All right, all that we do here is change the geometry. So I am so lazy. I am going to copy this line of code from here. I'm going to paste it down below because I'll tell you what, by the end of this lab, you're going to be so sick of tired of typing ggplot. It's much faster. All right, so geom jitter, and I'm going to set alpha, which is the transparency, equal to 0.6. All right, so see here, all I did was change the geometry. I made it from a point to jittered, and I said, make the transparency about 60%. Go ahead and run that. And now you can see where these points are clustered. So you can see them overlapping, you can see that these ones are individuals, and it's much easier to read this chart because you can now see where their points are layered on top of each other. They're very dark. Excellent. So we've shown 2 variables here, and that's fantastic, but it'd be really nice if we could encode the species, right? I'm going to guess that this is one species, but I have no idea what's going on here or where the breaking point might be. So I'm going to use color to differentiate the species. All right, so I'm going to copy this again, because again, I am very lazy. And here I'm going to change my aesthetic, and I'm going to add a variable to my aesthetic, and it's going to be color equals species. Okay, so go and run that. And excellent. Now we can see that our guess, in fact, was correct, and the red points over here are the setosa, and they are considerably different, or they're noticeably different from both the versicolor and the virginica, which are kind of mixed up together here. You know, green is kind of centered down here a little bit more, but you still have blues over here. Blue is kind of centered over here a little more, but you definitely still have greens over here. So there's not really an easy way to differentiate these two just by their sepal length and width ratio. Okay, but you really can tell the setosa. Excellent. All right, so that was great, but I have to say, I really don't like plots that don't have titles. This is feedback that I give everyone, not just in a class. So let's put a title on our plot. So I'm going to copy the exact same line of code here. And this time, I'm going to, after my geometry, add labs for labels. And I'm going to specify my title is sepal length by sepal width in iris dataset. Not terribly informative, but at least we have a title that tells me what this plot is about. Excellent. All right, so this is fine. However, we probably would do better to break these two apart, to break apart the versicolor and the virginica. And while we're at it, we might as well break them all apart and do what we call faceting. So faceting means breaking something into small multiples. And when you have overplotting, like we do here, where we can't really see the difference between these two categories, then faceting is your solution. Faceting is very often the solution. I am a huge fan of faceting. So let's go ahead and copy this line of code again, and paste it down here. And we are going to say, before our labels, we are going to call facet grid. I would argue that one of the strongest points of R is the ease with which it does faceting. All right, so faceting, or the facet grid function, has kind of a unique syntax to it. So you're going to call facet grid, and then you're going to go period, tilde, and then species. And what this says is facet grid by the variable species, right? So we still have our labels. Go ahead and run that. And it looks like I have an error. So if you look down here, I have made a typo, and it's actually a really great one, so I'm going to keep this in here. I forgot to put my plus sign, which is a problem that I have very often. So if you add a line of code into the middle of your sentence, you need a plus sign. Let's go ahead and run that. And then you get 3 plots. And now it's much easier to see here the trend in the versicolor and the trend in the virginica than it was earlier. We can see what's going on with each one of these different flowers. See that in fact the virginica is a little bit higher overall, but the versicolor is a little bit more tightly clustered and a little bit better correlated. All right, but not nearly as correlated as the setosa. Okay, so that was great. But as we were just saying, like, we're looking at this and we're thinking, hey, there's a trend here. What is that trend? And a natural next step would be to say, what is the line of best fit? You know, what is the ratio at each point for this relationship? So we're going to use something that's called stat smooth. This method is linear, so it won't work for things that are curved like that. But these all look like pretty linear correlations, so that should work. And when we call stat smooth, we also have to specify whether we want standard error. Standard error is how much off we think that line might be. We don't want that, so we're going to put standard error as false. All right, so I'm going to copy this exact same line of code. I'm going to add it down here. After my facet grid, I'm going to add stat smooth, and I'm going to say that the method is linear. The standard error is false, and I'm going to make the color red. You can make it whatever color you want, but I'm just going to use red. I'm going to remember my plus sign at the end of the sentence. Go ahead and run it. And now we get a line of best fit, or a line showing the trend here for each one of these plots. I have to acknowledge that maybe red is not exactly the most visually appealing. You might want something like gray, which is a little bit less garish, but also a little bit harder to see. So you can go ahead and play around with that. R will take a hex code there, so if you really want to play around with it, go for it. All right, so you may have noticed by now that this is beginning to get a little bit redundant. We copy this block of code, we paste it, we use it again. ggplot is super smart about that and actually allows us some more portable ways to manipulate our plots, so that we can try out different visualizations, we can try out different color palettes, we can try out different geometries, and things like that. So the way that you do this is you make an object, and then you port that object around. We are not going to use object-oriented programming in this course because, quite honestly, for getting things done, it is not necessary. If you want to become a developer, or if you want to work more deeply in a programming-related field, learning object-oriented programming is essential. But for us, you don't need it. And quite honestly, in my own career, I don't use it that much because it makes the code harder for novices to read. But this will make it a little bit easier. So we are going to use an object. We are going to call irisPlot, and we are going to set that equal to ggplot, where we pass the dataset iris. Our aesthetic is going to be x equals sepal length, y equals sepal width, and color equals species. So this block of code that we've been using every single time. So we'll run that, and we've just stored it as an object. We see here we have this new variable, and it's called irisPlot. Now we can really easily try out different geometries. So I'm going to call irisPlot plus geom point. I'm going to call irisPlot plus geom jitter. And I'm going to call irisPlot plus geom line. All right. This looks kind of crazy, but kind of cool. All right, so we're going to go through and talk a little bit about this. I'm going to go back through to our first plot. So this was our object irisPlot, and then we just added a geometry to it. And really, if you think about it, this is our core. So if you think about data visualization in a deconstructed way, then you have really size, position, and shape. Size, position, and color are the only way to visualize your data. You can do a lot with size, position, and color, but you can't do that much. And if we look up here at the structure of our object, we have the data, and then we have the position, and we've specified the color, even though we could do it externally. But we're going to hold these things constant, and then we're just going to do things like change the shape. So all that we're doing here is taking this core of a plot and adding a shape to it, which ggplot conceptually functions in this really cool way of layering things on a Cartesian plane. So a Cartesian plane is this XY axis here. Anytime you see a grid, you're looking at a Cartesian plane. And what the ggplot library lets us do is just keep adding layers. Just keep adding layers of visualization, layers of information to this core. But you always have to start with this fundamental core. And that's what we've done here. We have this data core, and we visualized it in this way. And I have to say, honestly, when you add the color to this, I'm kind of in love with this visualization just because it's like, looks very modern and very cool. Doesn't communicate what you want it to, but aesthetically I find it to be quite pleasing. So we have this one, we have the next one, the one that we jittered, and we see here that it's a little bit easier to read, but it's not quite as aesthetically pleasing as the other one. And finally, we have the lines, which doesn't actually make sense for this kind of a visualization, which is part of why it looks so crazy, because this is not a continuous variable. There's no relationship. We're not in a progression here. It's not like, you know, this is one thing measured at different time periods. Rather, these are different things measured independently. So this should really only be points or jittered. This should never be a line. This visualization does not make sense. All right, cool. So right now, the way that we're doing our jitter is kind of random. So the first time you used jitter was different from the second time that you used jitter. That's not exactly as consistent as we would like to be. We would like to make it consistent across all of the plots. So we're going to make a new variable. We'll call it POSN, standing for position. And we're going to say position jitter. And we're going to say that the width is 0.1. And all that this will do is make the jittering consistent across all plots. So what we're going to do now is we're going to call our variable iris plot. We are going to add to it a point geometry. And then we're going to say position of those points equals POSN. So we have embedded the jittering, we've embedded the shifting around in a consistent and systematic way within our point geometry. So we have altered our point geometry rather than calling the jitter directly. So this is just another option for how to make your visualization represent what you're looking for. All right, and I tried to run that without storing my variable there. Just make sure you run both of them. All right. And now, anytime that you call this plot, if you call it with the geom point and then specify that the position is a jittered position, that's 0.1 width, which is a mathematical representation in the back end that we're not going to get into, then across all of your plots, the amount that each point is jittered will remain constant. Cool. All right, so we're looking at this plot, and we've already found the lines of best fit. Now we might want to do something like put one point in the midpoint of each cluster. A point that is essentially the average of that type of flower. It can then represent that type of flower as like a stand-in for all flowers of that type. The average width, the average length. So we actually need to modify our data a little bit in order to get this. So what we're going to do is we're going to create a summary. And our iris summary is going to be columns 1 through 4. So that was our 4 numeric variables. And we're going to find the mean of each one of those columns. So first we'll call aggregate, and then I'm going to say aggregate for each column from 1 to 4. List for iris species. So don't don't aggregate within the species, keep the species separate, and then give me the mean for each one. So whenever you have a categorical variable and you're, we don't want the average flower overall. We want the average for each one of these categorical variables. We want the average of each type of flower, which is why we needed this list of iris species here. All right, so we'll go ahead and run that, and then we'll call names of iris summary. We'll call them 1, and we will assign that to species. Let's go ahead and run that. Nope. Names is not names. And this will store the names into this variable. Or rather, this has specified that for our summary, the 3 ways that we aggregate it are with the species, and they are all, it lines up because they're all in the same order to begin with. All right. Finally, we will call iris summary, and we just have 3 rows in it. We have the setosa, which its average length is 5.06. Its average sepal width is 3.42, petal length 1.46, and petal width 0.246. All right. So now that we have these averages, and we've manipulated it on the data side, we can go ahead and add these to our plot here. All right, so we are going to call iris plot again, and then we are going to add a geom point, and we're going to do position equals POSN, and we are going to add to this a geom point that the data for this point is going to come from iris summary. So notice how we're embedding a chart within a chart here. So this is one of the really cool ways that ggplot allows you to layer different plots on top of each other. So this base plot is going to stay the same, and we have our geometry for our base plot, but what we're saying is, hey, give me another geometry type, and in order to make that geometry type, use a different data set, which is pretty cool. So we're going to call shape 21. I looked that up on the internet. I don't know the shapes off the top of my head. Size is going to be 5. Again, you can just play around with that. And fill is going to be equal to hashtag 1, 2, 3, 4, 5, 6, 8, 0. All right. We'll go ahead and run that. So this fill is just the fill color. This is a code that I got on the internet, so don't ask me how you find those. You just go to the internet and search for them. Same with the shapes and the sizes. You can also ask for help from the geom point. You can probably get more information here. Yeah. So all of this is going to be in the documentation, so you'd go here and then hit F1 and you'd get more documentation. All right. So what we did is we layered a chart on top of our existing chart, which is just really cool. So here we have the average setosa, the average of the versicolor, and the average of the virginica. And we see that actually the versicolor and the virginica from this data set are quite different, which we might not have been able to fully see just looking at the data here. Excellent. All right. So we are now going to analyze these same data points, but with lines. So maybe rather than seeing a point here, you'd rather see a line to see what is greater than and what is less than the mean or the average. And the way that we're going to do that is with V-line and H-line. So again, we'll call our iris plot. And we are going to add our geom point and our position equals POSN. We're going to add to that a geom v line, and we're going to say the data should come from the iris summary rather than the iris dataset itself. And the aesthetic on that is going to have the x-intercept I always forget how this gets written. Yep, x-intercept is going to be the sepal length. All right, so I'm going to go ahead and move that to the next row. So we have our geometry point here that we've been using before. We have our vertical line that has an x-intercept at the sepal length. So go ahead and run that. And now you can see that for the setosa, you have the vertical line here, for the versicolor here, and for the virginica here. So you can see which ones are above and below that line. If you want to do it with both, it's actually quite easy. We are going to copy this line of code here, paste it down here, and then we are going to add to that geom hline. And we will pass data equals iris summary, and the aesthetic this time, as you might have guessed, has the y-intercept equals sepal dot width. Excellent. So we'll go ahead and run it, and you get a cross mark for each one. Not quite as useful as you might want it to be when you have 3 different plots. So I would probably facet this, facet grid, by species, run it. And that's quite a bit better. Much easier to see when you're using the horizontal and the vertical lines, that each independently. Also a little bit easier to see here how they're kind of different from each other quite a bit. All right, great. Also, I would argue that these like very solid lines might be not quite what you're looking for when you're looking for these trend lines. So we can go ahead and change the lines. I'll show you that really quick. Copy this exact code over again. You might want to save this into an object if you're working with it a lot. And here you can say, after your iris summary, you specify that you want the line type to be 2, or maybe you want the line type to be 3. Line type, there we go. Which just gives you different kind of lines, different kind of trend lines. Sometimes that's a little bit easier, especially when you're using these graphs for communication with someone other than yourself. So if you're using these graphs in order to publish them, then you would want to use different types of lines for trend lines like this. Which leads us into our next point. Up until now, our plots have been strictly exploratory. You can go ahead and distribute graphs like this, but it's very likely that you're going to want to alter your formatting in order to better tell your story. At this point, I'm going to start copying and pasting a lot of code because I've written it once and I hope to never write it again. It's very many specifications, so we're going to walk through them, but I'm not going to type them in front of you. All right, so the first thing that we are going to do is we are going to add some coordinates and we are going to specify the scale. We are going to add back in our line of best fit. We're going to remove our vertical line. So I will show you what we've done to do that. So we have our iris plot that we've been having this whole time. We have our geom point. Our position is our position. Our alpha is 0.5. We've added back in our facet grid, added back in our stat smooth. And here we have added a y continuous scale, which will be this scale, and an x continuous scale, which will be this scale. And I've specified equal coordinates. So let's see what this does. All right, so it made it way smaller and probably not that much better, but at least like a little bit more square. Okay. First off, I don't know why I did this in red. I'm going to put this back to gray. Okay. So what this says is for our scale continuous. First, since it's a scale, it knows that this is going to be a label. So we have our sepal length, our sepal width in centimeters. The limits are from 1 to 5, since 1 will more than sufficiently cover all of our data. We say expand from 0 to 0, and what this means is that none of the data and the axes will overlap. So this makes sure that there's no overlap, like the data is not off of the plot in some way. All right, we have similar here for our x continuous, so our continuous x scale. The only difference is that we've added here some breaks. So up here we had every single integer was a break, but here we want to start at 2, we'll get to that in a second, go up to 8, and increase by every 2. All right, so here we've made our limits from 4 to 8, but we've told our breaks to start at 2 and go to 8. Well, limits controls your scale more than any other factor here. So if you specified that your limits are from 4 to 8 and you've said, hey, start my scale at 2, it's not going to do that. It's going to start it at 4 because limits are the controller of the scales. All right, and we have the same expand out to 0 to 0 to make sure that the data and the axes don't overlap. All right. Last thing that we're going to do is add here the coordinates equal, and what this does is it just makes sure that all of our coordinates are equally spaced, which is the expected behavior. All right, so we are going to move along, and you may have noticed while we were doing this that one of the things that I hold really, really dear about plots is actually missing. So we are going to go ahead and add the labels here. We'll run this, and all that we added to this was that our title is sepal length by sepal width in centimeters. All right, so I have to say this is getting kind of annoying to type this out every time. Rather than typing it out over and over again, what you can do is specify a theme. So that is how we are going to work with this now. So ggplot, or R, as I actually think it is in ggplot, allows you to specify a theme in the exact same way that you specified the base plot. So the theme you can carry around and bring with you over and over again. So we've specified a theme here. I'm going to go through, we have the same thing that we've been having. We have the iris data set, we have our aesthetic, our geometry, we've faceted, we've added our regression line, we have our scales, we have our title, and now we're going to add this theme. So honestly, I have never written a theme from scratch. I've just modified other ones because it's a whole lot of text then and very like small specifications. And unless you do this every day, I don't see why you'd remember all these specifications when it's really, really easy to just find them already written out by somebody else who ideally was involved in writing the documents. All right, so what we got here is this theme. And our theme says that the background should be blank, the plot background should be blank, the legend background should be blank, the legend key should be blank. The only thing that we have really specified here that's not blank is the axis text is going to be black, and the axis grid marks are going to be black, which I think is what they are now. The panel grid, which is the major grid lines, are going to be blank. The axis line is going to be black, which is just the axis along the edges here. The strip text is, I honestly don't even know, but when you pull these down, it usually comes in all together. I'm sure we could edit that and figure out what that is. And this panel spacing, which is the spacing between each one of these, is going to have lines. Okay, so we are going to run this whole block of code here. And you see that it's actually changed our grid quite a bit. Notice that up here in our aesthetic, we no longer have color. So since we are differentiating by the 3 plots, we don't actually need color. It's just kind of redundant. And it looks much more, I don't know, this has a very different feel to it. Here are our axis lines that are now done in black. And here are our tick marks that are done with black. And you see, this is what we mean by the panel grid. So whereas previously there was kind of a grid that you could see behind each plot, you no longer have that grid. And that, I mean, I would argue that this looks a whole lot cleaner, but you know, you may argue that you want to have those grid lines so that people can figure out the exact data point a little bit easier. All right, so that is a whole lot of text. We would never want to use it again, so we would specify it. We would say our iris theme is all of these specifications. Our background is blank, our plot background is blank, our legend is blank, our legend background is blank, all of these that we went through earlier. You'd call those together and define them as a theme and hold into it in the memory. And then if we come down here and we specify our base plot that we specified before, we add our geometry, we specify our title, and we give it the iris theme. Sorry, I forgot that without this we don't have the faceting, but as an example, so this is the same theme that we used before, but this time we have our colors. We don't have our linear regression line because we didn't specify it, but what we do have is the same style or the same feel. So in one plot you might want to break them apart because you're making one point about the regression or the slope of each of these lines or something, and then in another plot you might want to have all of the points like we did at the beginning in order to make different points with each one of your plots, even though they are very, very similar. So the themes can get a little unwieldy, which is why, as you may have guessed, there are some built-in themes. And you can find out what these are by typing $GG themes, running that, and you can get the entire list of themes here. We loaded GG Themes library at the beginning of the lab, and with the GG Themes library come really cool things like, let's say, the Tufte theme. If you're not familiar with Tufte, he is a great place to start for just really getting a sense of the design considerations even. All right, so let's take a look at the Tufte theme. We have our iris plot, we have our geometry, we have our title, and now we're going to call theme Tufte. All right, and all right, let's see how that looks. Excellent. And you'll notice that the Tufte theme has this serif font. It has no lines whatsoever, super minimalist, which is kind of Tufte's entire perspective, that anything that doesn't communicate some sort of information is something that you shouldn't have in your plot. All right, so after this, go ahead and choose either the categorical variables with chicken weights or time series with air quality labs. Be sure to submit your
plot that you made. You can submit it with the Tufte theme or you can submit it with the Iris theme. Doesn't really matter. Just go ahead and submit your plot for this one, and I'll see you in the next lab. All right, good luck. Bye-bye.